Okay, good day, everybody. Today I'm going to discuss some solved problems in statics. So the first problem, a heavy uniform bar AB rests in equilibrium in a rectangular ditch with smooth surfaces. So determine the inclination theta of the bar to the horizontal. So this is the given figure, and let's draw the free body diagram of the heavy uniform bar. Since the contact surfaces are smooth, then the normal reaction at A would be horizontal. So we have the action force, which is the weight of the bar, and it acts at its center. So its distance from B or from A would be 4 meters, which is half of the length of the bar. So normal reaction at A, then we have the normal reaction at C, which is perpendicular to the length of the bar, and the angle that N sub C makes with the vertical would also be equal to this angle and inclination theta. So as I said, the weight of the bar is 4 meters from B, also 4 meters from A. So this angle is also theta. Remember the principle. Then the horizontal distance of the weight from NA is equal to 4 cosine of theta, because 4 cosine theta. So this distance, the distance of C from A is equal to, because this is 2 meters, 2 over cosine theta, or simply 2 secant of theta. And of course, the horizontal distance of the weight W from A is 4 cosine of theta. So first, let's sum up forces. Uh, Vertical equals 0. So so that we can express N sub C in terms of W and theta. Then our second equation would be, equilibrium equation would be, we sum up moments about point A equals 0. Then from there, we can solve the angle theta, because N sub C is in terms of W and theta, and we can cancel W in that equation. So summation forces vertical equals 0, upward positive. So we have N sub C cosine of theta, the vertical component of N sub C. Then minus W equals 0. So that means N sub C is W over cosine theta, or W secant theta. Call that equation 1. Then summation of moment about point A equals 0, considering counterclockwise as positive. So we have N sub C times 2 secant of theta, the moment arm, then minus W times 4 cosine theta equals 0. So replacing N sub C by its equivalent, which is W secant of theta, and transpose 4 W cosine theta to the right. So we can cancel out W, and note that 2 divided by 4 is equal to 1/2, and we have cosine theta divided by secant square theta, since secant square theta is 1 over secant square theta is cosine square theta, so 1/2 equals cosine cube of theta. That would be the simplification of the upper equation. So solving for theta, theta is the inverse cosine of the cube root of 1/2, and that is equal to 37.47 degrees. So that's the solution to the first problem. So let's proceed to the next problem. So problem 2, the boom BA supports a load of W equals 5,000 newtons. The boom is held by a ball and socket at B and by cables AC and AB. Neglecting the weight of the boom, calculate the compression in AB and the tension in cables AC and AB. So this is the given figure. So actually, we can just set up equation summation forces x equals 0, summation forces y equals 0, and summation forces along z equals 0 because all these members are two force bodies. So, in, but I'll present a solution which is taking the sum of moments about a certain axis equals 0. So let's apply the reaction forces and the components of the tension especially. So these are the components of the reactions at B. And remember that BA is a two-force body because the weight of the boom BA is negligible or neglected in this problem or not given. Then the components of tensions at C. So those are Cx, Cy, and Cz. These are the components of the tension in AC. Then at D also, so we have dx, dy, and dz. So first is we sum up moment about the BZ axis equals 0 and applying the right thumb rule, and take note that points C, D, and B lie on one plane, and that is the YZ plane. So that if we sum up moment about BZ axis, the Y component of tension passes through the Z axis for CY and DY. They all pass through the BZ axis, so they are not involved in the moment equation. Then only CX and DX are involved because CZ and DZ are parallel to that axis, so they are not involved. So summation moment about BZ equals 0. So following right thumb rule, our equation would be Cx times 3 plus dx times 2.4, then equals 5,000 newtons times 3.6. Simplifying, 3cx plus 2.4 dx equals 18,000 newtons. Call that equation 1. Next is we sum up moment about the by axis so that we can relate cx and dx. Uh, uh, CZ and DZ are not involved because they pass through the BY axis. So by right thumb rule, BX times 1.8 minus CX times 2.7 equals 0. That would be the equation that can be formulated. So expressing DX in terms of CX, so dx is 1.5 of cx. Then we substitute this into equation 1. 3cx plus 2.4 times 1.5 cx equals 18,000. So from there, cx can now be solved. It is 30,000 over 11 newtons. Then dx is 1.5 of 30,000 over 11. So that would be 45,000 over 11 newtons. So knowing the components of tension at C and D, the x components of tension at C and D, we can compute now the tension by the equal ratio, which is Cx as to the x distance 3.6 equals tension in AC as to the length of AC. So the length of AC is square root of 3.6 square, then plus 0.6 square, 1.5 square because 3 minus 1.5 is 1.5, then along Z is 2.7. So again, 30,000 over 11 as to 3.6 equals tension AC as to distance AC, which is 3.6 square plus 1.5 square plus 2.7 square. Solving for tension in AC, it is equal to 3,593 newtons. Likewise, by similar ratio, dx as to 3.6 equals tension in AD as to distance AD. Distance AD is square root of 3.6 square. Along Y is 2.4 minus 1.5, so 0.9 square. And along Z is 1.8 square. So 45,000 over 11 as to 3.6 equals tension AD over square root of 3.6 plus 0.9 square plus 1.8 square. So solving for tension in AD, it is equal to 4687 newtons. Then finally, for the compression in member BA, we only need BX. Then we apply similar ratios. So summation forces x equals 0. So BX equals CX plus DX. So BX equals 30,000 over 11 plus 45,000 over 11. So BX is 75,000 over 11 newtons. Then by equal ratios, Bx as to 3.6 equals uh, force in Ba as to square root of 3.6 square plus 1.5 square plus 0 square. There's no z component for Ba. So finally, Ba is equal to 7386 newtons, and it is in compression. So these are tensions, so understood tension. So finally, we proceed to problem 3 about internal force systems. So this is the problem 3. Determine the internal force systems acting on sections 1 and 2 for the pin-connected frame. The sections are located just above and just below pin C. So this is the figure. So actually we can solve directly the internal force systems in section 1 because we can separate uh, the portion of the member from D to 1 as a free body. So these are the expected component reactions at B and at A. So because the external load is a couple, then we conclude that By is equal to Ay in magnitude, but they are in opposite directions. Similarly, Ax and Bx are also equal to each other. And actually, because member BC is a two-force body, it is only bounded by smooth pins and there's no load in between. Therefore, this is a two-force body. So the reaction is directed, for reaction at B, it is directed towards C. Likewise, the reaction at C is directed towards B. And because this is a quarter circular arc, so we conclude that the component reactions By and Bx are equal. So it follows that Ax and Ay are also equal based on the free body diagram of the entire body. So let's consider first the reactions. So let's solve for reactions for the reaction By. Summation moment about A equals 0. We can solve for By. And remember, By is equal to Ay. The only difference is Ay is downward. So By times 0.5 equals, because this is a couple, so 300 times clockwise couple, so 300 times 0.4. So By times 0.5 minus 300 times 0.4 equals 0. Or if you sum up moment about A, it's the same as 300 times 0.9 minus 300 times 0.5. So the net value is 300 times 0.4. So solving for By is 240 newtons. And because using the general free body diagram, there's no other vertical load, so we conclude that Ay is also 240 newtons. So this is the free body diagram of this two-force body BC to show that uh, Bx is also equal to 240. Remember, that's 45 degrees. Uh, the components Bx and By must be equal because this is 45 degrees. Or the other way is you sum up moment about C. So Bx times 0.5, that's clockwise, equals 240 times 0.5 counterclockwise. So cancel 0.5. So that proves that Bx is also 240 newtons. So Bx, considering the entire system, we conclude that Ax equals Bx because 300 and 300 will cancel, will vanish because they are equal. So Ax equals Bx is also equal to 240 newtons. So first, let's draw the free body diagram of the portion B to section 1, D1. This is the free body diagram. So therefore, the internal force system here consists of the normal, N1, the shear force, which is obviously leftward to oppose 300 newtons, and the moment, which is counterclockwise, M1. So obviously, if you sum up forces, vertical equals 0, so N1 is 0. So then summation forces X equals 0, so shear 1 is equal to 300 newtons. Then summation moment about section 1 equals 0, so M1 counterclockwise minus 300 times 0.4 equals 0. So M1 equals 300 times 0.4, or M1 equals 120 Newton meter. We can now isolate as a free body from A to section 2. So consider free body diagram of A2. So note that BC is a two-force body, and I already demonstrated it here. So that AX equals AY 240 newtons. So this is section 2. The forces consist of N2, shear 2, which is leftward to resist the rightward force, and the moment is clockwise, M2. So summation forces Y equals 0, so obviously N2 is 240 newtons. Summation forces X equals 0, obviously the shear 2 is equal to 240 newtons also. And summation moment about section 2 equals 0, so M2 minus 240 times 0.5 equals 0. So M sub 2 is also 120 Newton meter as shown in the figure. So that's the complete solution to this problem. I hope that you have followed the solution, and I want you to solve more problems on equilibrium systems and include this internal force system.